Humans can combine and use many types of sensory information. Even when one modality is noisy or missing, we're still able to accomplish amazing feats of dexterous manipulation. This ability is also known as cross-modal compensation. The question is, can we endow robots with the same ability? In robotics, different sensor data can become corrupted during deployment. Assuming that only one sensor can be corrupted at a time, we introduce our novel method, Cross-Modal Compensation Model, or CCM. CCM can compensate for corrupted sensor inputs in 3 steps. The first step is to detect. In this example, CCM detects that the image is occluded. CCM then rejects and discards the corrupted image input. Lastly, the depth and force data enters the CCM fusion module, which corrects for the rejected image information. We will now go over how CCM is able to correct for rejected modalities. CCM is a representation learning model that takes an image, depth, force, as well as robot proprioception as input. Our input modalities are fused together in a latent representation, which we will call Z. To teach CCM how to correct for rejected inputs, during representation training, we randomly drop out sensor inputs to generate our compensated latent representation, Z'. We introduce a latent distance objective that minimizes the distance between full modality Z and compensated Z'. We also train CCM using self-supervised objectives that prior work have demonstrated to be important for representation used in manipulation tasks. Lastly, we train to reconstruct our input modalities, a commonly used training objective. In this case, reconstructed modalities also help us detect when an input modality is corrupted. We only train our representation with normal uncorrupted data. CCM is able to reconstruct normal image data with low reconstruction error. However, if CCM receives a corrupted image input during deployment, there will be a high reconstruction error, which we threshold to detect when an input modality is corrupted. After training, we freeze the representation and train an RL policy. We use a peg insertion task to experimentally evaluate how well CCM has performed. After policy training, when CCM detects a corrupted modality during policy rollout, it uses the steps of detect, reject, and correct, and feeds the compensated Z' to the policy. In this example, depth is corrupted. We show that during policy rollout, if CCM does not compensate for corrupted images, it mostly fails to accomplish the task. If CCM performs cross-modal compensation on the corrupted images, the policy can accomplish the task 81% of the time. In addition to corrupted images, we also show that our novel method is able to perform cross-modal compensation on corrupted depth and force data with task success rates of 82% and 78% respectively.